My name is Jørgen. I am founder of Oslotre, where I today work as a creative director. I will give you a short introduction to the company, then I will talk a bit about modern timber architecture, and finally talk about two projects that we have recently finished. Our background is we used to run a CLT production in Norway between 2010 and 2015. Then we sold the machines in 2015, and or actually, when we started the CLT production in 2010, the CLT was quite a young material in Norway and not that much used. It had a rumor of being very expensive and also full of errors. When we started the production, we understood that it's actually not the material that's full of errors. It's what's being done in front of the production and after the production. Then we started the architect and engineer company, and we also started an assembly company. In this way, we could follow the product from start to finish, and try to kind of make it better and more economical. So we sold machines in 2015, and then we started Oslotre, which is an architect and engineer company. We work both as architects, but we also do a lot of the design to production. So we do all machine files for different companies in Europe. We've been doing this now been an architect company for 13 years. Worked with every typology in architecture, from houses and cabins to office buildings and apartment buildings. Since 2020, we have been working in Australia as part of Timber Design Studio. This is a collaboration between architects and engineers from Europe mainly, and we have been working extensively with CUSP, building some of the first hardwood CLT buildings in the world with CUSP from Tasmania. We also worked a little bit with the Australian Pavilion as advisors for the Dubai World Expo, and we have been working a little bit with the Atlassian headquarters in initial stages, working as advisors on the use of timber, the planning and logistics with timber, acoustics, fire, timber engineering, and so forth. But mostly we work in Oslo, in Norway. That's where we work from, and then we work all over Europe, but mostly in Norway. And we are today two companies. We are HasleTre, which translates Oslo Wood, which is the architecture and construction technology part, and then we have Oslotre, which translates Oslo Prefab, and which is our assembly and carpentry unit. So we have built and designed and built a lot of smaller projects. All of our small projects we mainly build ourselves. In this way, we have control of the detailing, and we also, our architects learn from this, so we don't do the same mistake various times. So we build in every scale, really. And we always try to adapt our architecture to nature. We don't try to adapt the nature to the architecture. As we can see here, we are trying to fit to this rock that was already on the site. This combination of automatic production and nature, and how this can play together. We also work on the larger buildings. This is number 4. I will talk about that a bit later. This is also a 5-story apartment building in CLT that we recently completed. This is a culture school also in CLT that we also recently completed. But I think before talking about our works, I will talk a little bit about our philosophy around timber architecture. And we are now in what the scientists call the Anthropocene epoch, which is a geological epoch where human influence significantly alters the Earth's natural environment. So this is actually the first time we have been able to alter the Earth's environment, which is quite massive. And the reason for this is basically that we are now estimated in 2050 we will be 10 times as many people on Earth as we were 200 years ago. So with this massive explosion of people in a very, very short time, we also see this massive explosion of greenhouse gases, but also building down of nature. So only since 1960, we have reduced the population of animals on Earth with 69%. And the building industry is part of this. Excuse the Norwegian in this slide. It's the building industry stands for about 40% of the climate gases globally, and 50% of these are from materials. And where does the materials, which materials do we use? It's mainly concrete and steel. Concrete is today, after water, the most widely used substance on the planet. It is estimated that around 2040, the total produced weight of concrete on Earth will be higher than the total weight of all living biomass on Earth. So all the birds, all the fishes, all the animals, all the trees, all the plants. So in a pure mass flow sense, the human civilization is essentially can be seen essentially as a machine for producing concrete and gravel. That's what we bring to the table. So in Europe, the European Union and Ursula von der Leyen, the president of the European Union or Commission, she had her speech to the European Parliament in 2020, where she is introducing what's called the European Green Deal. So the Green Deal is that EU aims to become the world's first climate neutral continent. This is, according to von der Leyen, it's going to be done with artificial intelligence, and it's going to be done with organic building materials like wood. To make this possible, it's introduced something called the taxonomy, and the taxonomy is basically if you're going to build in the future and get good premises on your loan, or what's so-called green loans, you need to comply with this taxonomy. So this is now been introduced in Europe, and it's also the start of what I believe will be a very, very big shift in our construction industry. And it's a shift towards using materials that are on the lower part of the material pyramid. Basically, all the materials that are under this red line, they are carbon negative materials, meaning that they actually store more carbon than what they release during production. And the more synthetic a material is, the higher the CO2 emissions usually are from that material. And what's under this red line? It's mostly wood and some plant materials. So that leads us to today's topic, which is modern timber constructions. Basically, the tree in the forest, it's a very intelligent machine, probably the world's most intelligent machine. And through photosynthesis, the tree captures CO2, or it captures the carbon from the air and stores it and use it to grow. It stores it in the wood trunk and produces sugar, and as a byproduct, it also produces oxygen, so we can breathe. Timber, it's very light and strong, but it's also very formable. So when we format timber in a production, the use of energy is actually very low. It's a very energy. It's not using much electricity to produce, and so when we have a finished produced timber material, it actually has a negative carbon footprint. It has 0.7 tons of CO2 stored per cubic meter of wood. None other building material can do this, meaning that we can use the trees as carbon captures, and we can use the buildings and the cities as carbon sinks. This is a technology that exists today. It's present, and it's possible to introduce quite rapidly into the market. Maybe in the future we will invent even smarter solutions to handle our climate issues. But today we have this solution. This solution is ready for us today. But the important part to be able to make this work is that we run our forest in a sustainable way. So for every tree we take out, we also need to plant more trees and kind of make this short carbon cycle material solution run. So here we talk about carbon cycles that is maybe between 100 to 1,000 years. Today, the tallest building in the world is Mjøstårnet. It stands here in Norway. It's 85 meters tall, a pure timber building. But if you look back in history, actually, some of the oldest timber buildings, or the oldest buildings we have on the planet, are timber buildings. So this, the Todaji temple in Nara, outside Kyoto in Japan, which is 1,300 years old. It's 48 meters tall, so it's only actually 30 meters lower than what is today the world's tallest timber building. But it's extremely old, and actually it used to be 3 times as big, but it burnt down 1,300 years ago, and then they rebuilt a copy only a third of the size. The interesting about this ancient architecture is that it's all built with only timber to timber connectors. It's not a gram of steel or aluminium in this building. It's all held together with timber. If we look at the sail ships from the 17th century, these extremely advanced timber structures, probably the most advanced timber constructions that are ever made, were sailing on the 7 seas. Then the builders, they had the knowledge, they could go out in the forest and they could actually pick the tree before they took it down. and already know what they were going to use it for. That knowledge we don't have anymore. But now with the use of artificial intelligence, we are starting to see new ways of using timber. As here, the MIT Digital Structures Group are working on using wooden forks as joints in the buildings. This is where the timber is at its strongest, and can be a very interesting way of joining structure. So what we're actually seeing growing out of this is what we call biomimicry. So it's basically how we can look to nature and the complexity of nature, and how to solve, how to use kind of the nature's energy and material efficiency to make new architecture. But for now, we are mostly working on a two-dimensional level. We're working with optimized productions, super precise, under millimeter precision on the constructions. And the reason for this is actually the kind of how the involvement of the BIM modeling, the building information modeling for the architects, engineers, and advisors, and how this is also developing together with the automatized productions in the CLT and glue lamp factories. So now basically the machines, they talk together, the conversion from CAD to CAM, and we are getting this extremely high precision on the building materials. This again has paved the way for a new way of prefabrication. So basically what we get is a flat packed dry building system that's very fast to assemble, and it's also giving us the possibility to plan the building site in a whole different way. Basically most of the building is happening off-site. It's happening on the drawing board. Everyone is working in the BIM model, and we're producing a digital twin. Then the materials are produced off-site and then assembled together on the building site, meaning that we can, for the time being, we say that we can build twice the speed as you can do with the steel and concrete system. To be able to get there, we had to solve these three main issues, which are acoustics, fire, and water. Timber is quite light, so it has different acoustic requirements than what you are used to from concrete structures. Timber also burns, but it burns very predictably. It burns with 0.7 millimeters per minute, meaning that we can use parametric modeling to module how a timber building will react in the fire. Also, timber is not so fond of water, but at the same time, these are quite massive structures, and we are not that afraid of water anymore. So we're not building with these tent structures anymore, because we're building so fast that we don't see water as an issue. So actually what we do, we use water as a feature in the building, because we are working with biological materials in the interior of the building, meaning that we can use the hygroscopic properties of the timber to lower the need of mechanical ventilation systems, and where the wood is actually helping with the relative air moisture in the room. We also work a lot with what's called hygrothermic mass, where the timber is basically working as a low-tech heating battery. So when timber is dry, it is storing energy, and when you introduce water or moist in the air, this energy is released from the timber to the air. And in this way, we are actually now seeing that we can use timber to heat up our buildings. But to be able to do this, we need to learn how to detail timber. Timber that is detailed correctly will last for thousands of years. But then, I mean, the untreated timber is probably the best way to treat timber. But if you want to treat it, then we should treat it with products that are diffusion open, meaning that the timber can breathe and still be active in the environment. We also see a lot of science concluding on being close to nature is good for our health, both our mental health, our physical health, and especially our stress levels are shown to sink quite greatly when we are either in nature or smelling nature, actually. So what Jørgen studies from Japan, they show that actually the photoncides, the smell of pine and spruce are the defense systems of the tree, is actually working also on our immune defense system, making us healthier. So it's a study from Norway in the 90s by Professor Tove Fjell, where she concluded that having plants in the interior, it will lower the level of neuropsychological and muscular related alignment. So basically, sore throat and coughing, headaches, and so forth are lowered with plants in the interior, lowered as much as 23%. So since the 2000s, we are also seeing quite a lot of studies of having timber in the interior of buildings. And a study from Oslo in 2011 showed that children in a school room made of timber actually had 6 heartbeats lower per minute. So a significantly lower stress level. We also see from a study here in Norway from hospitals that patients that are admitted in the rooms with clad in timber, they are released from the hospital much quicker than the ones that are in rooms made of plastic. Also, we see wooden interiors in office buildings that are, we see fewer colds, faster back from illness, better concentration and focus. So to me, this says, okay, if you're going to build a new office building and you can, okay, do you want last century's solution with plaster, steel and concrete? Or do you want this century's solution with timber? And you also, as an addition, you get 23% lower sick leave. I think the choice is quite obvious. There's quite a lot of studies on this now, and also now as the Americans are starting to work with mass timber, they are also reproducing a lot of these studies to see if they can conclude in the same manner. So this brings us to HasleTre, which is the first case study. HasleTre is it's a demountable and reusable office building. It's now the house for Save the Children organization in Norway. And the background from this is basically if we see in a 60-year perspective, that the production of a building, this red column, is the main source to climate emission in the lifespan of a building of 60 years, which is a very short lifespan, but that's what we operate with. But if you look at commercial buildings, we have this yellow column. This is basically the changing of tenants in the space. So every time a tenant moves out of the space, which is maybe with 5, 10, 15 years intervals, depending on the company, a new company comes in, and it's they want a complete different plan solution. They want different interior and so forth. So all the old furniture and interior is torn out. It goes straight to landfill, and then new materials are produced to make new interiors. And in a 60 years perspective, this is actually even higher source of climate gas emissions than what the original production of the building was. So the aim with HasleTre was to make a building that could be demountable and reusable. So all the materials that go into the building will have a second life when they come out of the building and be able to be sold on the second-hand market. So they need to have a value throughout the building's time span. It's a BREEAM Excellent building, 3,000 square meters, gross floor area. It's a 4-story office building. Oslotre, we have had the role as architects and structural engineers on the building. It has won recently numerous prizes, which we are very happy for. So basically the facade material was chosen due to this neighboring building, which is called the Wine Castle. That's the old storage facility for the Norwegian wine monopoly. This expressive brick facade we wanted to kind of introduce to the timber building. So then we're using wood shingle. Wood shingle we know from our stave churches that have been standing outside for 1,000 years. And where usually the roof is clad with wood shingle. Here, every shingle will get its own expression with time, and in this way, it will look more and more as the brick facade on the mother building. When we make a plan like this, we always start with a grid. So here we have a grid that is 5 by 5 meters. It goes up with CLT production, where you can use the master element from production, which is 3 by 15 meters. This also fills up the lorry, so we can maximize the transport. And as timber weighs only 1/5 of concrete, but that means that we can use 5 times as few trucks to the site. We also assemble much quicker with these huge elements. It also gives the possibility to have a very flexible floor plan for office, just for meeting rooms, teams rooms, open plan, cell offices, and so forth. On the roof, we have a biotopic roof. That's the layer of earth that we remove from the ground when we build a new structure. We put on top of the roof, and in this way the insects can continue to pollinate and do their day-to-day business. So the construction system, it's a glue lamp, column, and beam system. It is we have tried to fabricate it as little as possible to keep it as close to the raw production material as possible. And in this way, not penetrate the beams. So what we basically did, we instead we cantilever the beams into the center of the building. Then we place the 3 by 15 meter CLT elements on top, and then we put all the technical appliances in the center of the building. In this way, we don't have to deal with the issue of having to introduce the timber engineer in every decision made by the technical advisors. On top of the roof, of the floor, we have a data floor where we have electricity and lighting, making it more flexible for future tenants to have flexible plan solutions. And we also have this strategy of layer on top of layer without using glue, silicone, foam, all these crap materials. So basically, the wood structure, it's a complete 100% wooden structure, the building. So the primary construction is in timber. The isolation material is wood fiber, and the connecting materials are wooden nails and different timber connectors. Surfaces are either plywood or timber cladding. The first connector is the common beam connector. So the building was designed during Corona, so it was designed as a digital project. We all sat in our own homes, but we were also trying to convince the entrepreneur to use this solution. They were very skeptical in the beginning, and so what we did, we had our carpenters go down on our workshop, and they made this mock-up to show how easy it was, and then we filmed it, and then we sent it to the entrepreneur, and in this way convinced them to go for this solution. So basically what we do, you take beech dowels, it's a harder wood, and then we dry it down to 6% wood moisture. We knock it into the column beam, and the spruce glue lamp, it holds 12% wood moisture. Then this beech dowel with 6% wood moisture introduced, it absorbs the moisture, expands and locks the construction. Also for the CLT walls and slabs, we're using this swallow, what you call it in English, swallow tail connector. It's made of beech plywood, also knocked in and locks the construction. So basically, what we are left with is a primary and secondary construction system that are 100% made of timber. It's not a gram of steel or aluminium in this system. We then design the structure down to millimeter precision. We do this ourselves to be able to have control of the complete structure before it goes to production. So we have our CAD engineers, they are designing this, converting it from CAD to CAM, which means computer-aided design to computer-aided machining. It then goes to the building site. Here we see the column, the beam tread on top of the column. We have the dowels that are knocked into the beam. You can see from this video the speed of this. Actually, the assembly team, they estimated that the building would take 8 weeks to assemble. They used 4.5 weeks with this system. Here we see the 3 by 15 meter CLT element, and also look at this perforation here in the element and the precision we are working with when we are assembling this building. So we're actually working with a furniture assembly precision on primary constructions in a building. So this is kind of the genius of this new engineered timber way of building. The precision makes it possible to build much faster, because we are designing this digital twin that is produced by a machine. So it's hardly ever a mistake in the elements, meaning that we can work on a much higher precision than what the building industry have been used to. We're using concrete and steel. Here we see the connectors for the floor elements. This is replacing thousands of screws that would have to be cross-screwed in this line, and it also spares the building workers from being on their knees for weeks putting in these screws. So here we see the primary construction up. It took 4.5 weeks. One assembly team. One assembly team is four people working normal hours. So it's extremely quick and efficient. Here we see this technical corridor. We see the technique that is put into the building. We also reused a lot of the technical installations in the building. So the ventilation aggregates are reused. All the bathroom furniture is reused. Some secondary rooms, we have reused carpets and so forth. Here we see these big bags that are actually waste from another building site, a building that was torn down. We're using these mineral wool acoustic plates on top of our timber structure. So all the acoustic material in the building are actually reused materials. The facade modules are made of timber, prefabricated, isolated with wood fiber, and clad with this wood shingle. The windows are also made of wood, a koya, so that's a way of treating wood that makes it last long. These windows are also possible to open, which is not very common in an office environment, but it's possible when we work with organic materials in the interior. We also see these cork elements. They are part of the acoustic strategy. All the interior cladding is with ash veneer connected with beech nails. These beech nails are shot in with a nail gun, and the friction when they are shot in activates the lignin. So the lignin, it's the binding material in wood, and when this is activated, it melts into the structure behind and keeps the elements together. This is also the part of reuse here, is that this can be just taken out of the wall, then we cut off the wooden nails, and we have complete elements without aluminium screws. There we see the walls connected. The surfaces, the timber surfaces are treated with hard wax oil, and on the floor we have a cashmere goat hair carpet. It sounds very exclusive. It's actually not. It's not more expensive than a plastic carpet that is more usual to use. The interesting thing about using hair in the interior is that keratin, that's what hair is made of, is actually encapsulating VOC. So it's encapsulating polluted emissions, polluted air, and actually helps to clean the air in the room. Opening up for this hybrid ventilation system. So basically what we can do is to have fresh air from the outside, and then we take the polluted air out in the center of the building. This we do by using biological materials in the whole complete structure. So basically this room we see here, it's 100% biological room. So all the walls, all the floors, all the ceilings are made of biological material. And this experience of coming into a space like that, this is very fascinating. It feels like the room is giving you a huge hug. It's so warm and quiet, and it really feels very fresh and clean always. And this is also what we hear from the tenants, the Save the Children organization. They are feeling a very high degree of happiness being in this building, and they feel safe and they feel warm. And this actually takes us to what I was talking about, about hygrothermic properties, because what we see in this building is that when it's 20 degrees minus outside, as it is in the winter in Norway, the thermostat in the building is down on 19 degrees plus in the building. which is way lower than we usually have in buildings. Usually you are up on 22 degrees. They say it's too hot. So, and even with 19 degrees, it's too hot. And this is due to the hygrothermic properties of wood, where the wood is working as a kind of a heating battery, helping to heat up the building. Yeah. So we're actually doing a lot of studies on this building now, and I think in a year or two we will have quite good knowledge of these functions. Toilets also made of timber. This is a Finnish startup called WoodSolutions that are making composite toilets made of 80% wood, 80% resin, now 20% resin, which will in 3 to 5 years be replaced with lignin, so it will be 100% biological material. Yeah, I see I'm running out of time, so I will speed a bit through these buildings. If you are in Oslo, please contact me and I can show you the building. The building took 6 months to construct above ground. It has 60% greenhouse gas reduction, has 80% reduction in steel usage, and is a 100% disassemblable and reusable building. Lastly, I will talk about Lumber 4. Lumber 4 is a 6-story timber building. Just recently won the building award of the year here in Norway. We have been architects and engineers on the building. Also done interior architecture on this building. 6-story building made of glulam beams and columns. The context, it's a historical timber site that's called Lumber, and that's then the reason for the name, where they produced plywood. Now it's converted into like a high-tech area for the sea wind industry in Norway. So the timber construction, it's a glulam column beam structure, and we are taking advantage of an existing communication core that we are connecting to. This gave us a very efficient construction process, and we see this building is raised in just one floor per week. We are using, for the floor system here, we are having longer spans. We are having up to 7-meter spans, and we're using what's called TCC floors. It's a timber concrete composite floor where timber and concrete works together as one unit. We have done this before on the Wood building that we were designing the timber structure in 2016, which is a 7-story pure timber building here in Oslo. I'm not going to say more about this today, but this is the first time actually in the world that this system was used in a large-scale building, and it has proven to work. And we are now introducing it in other buildings. So basically, what we do, we design the timber elements with these notches. It comes with these notches, and then we raise the timber building, and then afterwards you cast the concrete, and it kind of combines with the wood as one element. This also handles the acoustics and the fire. The exterior is painted green, and this is a treatment for the timber. So basically, this concave facade, sorry, the concave facade is was okay with the client, but they wanted a untreated. They wanted a facade that did not have to maintenance. So if we use core wood of pine, we can use untreated wood. But then usually we get this kind of drainage patterns under the windows. We didn't want that because we believe it looks very kind of dirty after a while. So we introduced a painted green. Basically, then what will happen is that the draining pattern will become a feature of the building, because this lower part under the window, it will not get the same sun exposure or rain exposure as the rest of the facade, meaning that the rest of the facade will weather much quicker, leaving these green circles on the facade. So the expression of the building will actually change with time. This is how the facade looks now. It's been up for half a year, so it's still not showing, but we're very, very much looking forward to this. And here we can see the concave facade elements, prefabricated elements, and the complete facade on the building. The system is also designed in a way that we can remove floors in the building. So all the floors are actually possible to cut out and remove, making the planned solution more three-dimensional. The wood interior, it's we're using as much exposed timber as possible, also for acoustic elements. And our reference, because this here, the client, it's on in a smaller town in Norway, and the economy in the building project is not so high, and so their reference was, okay, you have to build a building that doesn't cost any more than a steel and concrete building, and the reference to the interior is this extremely boring 19th century or 20th century office interior with plastered wall, plastic carpet, and gypsum ceiling. So that's your reference. Our solution to this is basically for the same cost to deliver a timber interior that looks like this. It has the same. It has nothing else than what's necessary. So all these elements you see here are for acoustics and fire purposes. But I will say that the difference between this interior and this interior it's massive, and this shows what's possible to do with low cost timber buildings. Here we see the atrium and this wooden escalator that is produced in one piece, lifted into the site, and some more pictures from the interior. The building is sequestering 700 tons of CO2 in the timber. It's also a competitive building with concrete and steel. We had actually two companies pricing the building, and the people pricing the timber were able to price it in the same price as steel and concrete. Yeah, so that's it from me. Sorry for going over my time, but I hope it was okay.
Not at all. That was incredible. Thank you so much for that really, really detailed presentation. I've got a ton of questions, and we've gotten a few great questions from the audience as well. I suppose we'll start with the first one that was asked. So I believe this is in reference to some of your earlier projects that you saw that you showed. The question was, how are services accommodated in CLT walled structures?
Well, I mean, the buildings are designed in a digital twin, and there we also solve all the technical appliances. So all the perforations are done by machines before we come to the building site, meaning that when you actually come to the building site, everything is solved. So you don't have to solve anything. You just have to kind of assemble all the structures. Also meaning that we get way less material loss because you don't have to cut anything on the building site. You can actually plan all the pipes and everything beforehand. So this is also one of the reasons why we see that the costs are going down, because all the different entrepreneurs are now seeing the risk is so much lower. But basically how we design it in, I mean, if you
is it mostly like behind the wall? Like, is it always a cavity solution, or do you sometimes run things within the actual mass?
Well, it's a massive element. So it's what we do. We then have to design kind of a cavity that we then cover up. So if you want to actually have electricity in the CLT wall, you should do it where the elements connect. and there we put in a cavity for it, or we can also pull the electricity on the outside of the CLT element on the warm side of the insulation, and then perforate through and in for putting electric cables and so forth. Yeah.
Another question here. What are the tolerances on the butterfly joints and the primary column to beam dowel connections?
Yeah. For the butterfly joints, we have tolerance. I think we have, it's not much. It's maybe 5 millimeters, I think. Yeah, and on the dowel solutions, we have about the same, I think.
5 millimeters sounds like a lot to still function.
No, it's not. It's not, because timber is always alive. So when you take the timber out of the factory and to the building site, the moisture level on the timber will actually expand, meaning that the structure expands. So we need to design in. So actually, 5 millimeters is very low. Usually, you design in maybe 15, 20 millimeters. Yeah.
You design those like on a large floor plate, like in HasleTre. Would you have like control joints that you check and then cut on site before it's lifted, or is that all taken into account in the CAD model with no modifications?
It's all done in the CAD model. Yeah.
That's remarkable. It's quite a journey that you guys have been on to start fabricating in a small shop, to build the team up, to get to a point where you're now consulting on the biggest projects in the world. Although it seems like it was always the biggest projects in the world, it's just that the projects gotten bigger as the world started to embrace this more. For example, that image that you showed of the CLT panel being dropped over that rock, how do you guys survey something like that?
This was something we did together with our interns. So we had some extra time on this. So actually we scanned the whole rock, and then we designed it in to the module and produced it. So it's actually not that high tech. I mean, with reasonably simple tools, it's possible to do quite high tech operations, scanning old buildings. And I also believe that a lot of new architecture needs to be based on old architecture. We have to build on top of existing buildings. So this scanning technology is very important to be able to kind of combine already built structures with high tech produced new structures.
Yeah, we've seen a few projects like that occur in Australia, and that infill development is something that everyone's looking towards to solve this, to generate more housing. I've got a question about the timber in the shower, which is something that is very, very cool. We've seen Western red cedar in hot tubs for years. Will we ever see swimming pools using mass timber?
I don't know. Maybe we have to ask the Japanese. They are the ones who know how to do this.
How big is the assembly team that's associated with Oslotre?
Well, actually, we have 3 guys that are now full time.
Right.
So it's a Swiss carpenter that's leading he's a carpenter and an engineer. He's leading the team. Very, very professional guy. But then we also have quite a lot of farmers, friends of us that are farmers, and that joins us building in the winter, because in Norway the farm is 6 months a year. You cannot do farming, so then they join us when we have larger assembly projects.
Right, of course, and I imagine that seasonality is responsible for a lot of the time pressures you experience in construction generally.
basically here, so outside here now, it's I think it's 14 degrees minus, and it's very difficult to build. It's actually very good time for assembly, but it's because it's quite dry and cold, so it's a good time for assembling timber, but it's not such a good time for doing groundworks. So usually the building season in Norway is mainly from March to October.
It's really short. But I imagine that at that time, in views, it means that you have to be quite disciplined with your program versus in Australia where we don't need to be quite so disciplined.
Well, it's been the same here, but I mean the shift is basically from building on site to building off site, and this is a massive shift in the way of thinking and building sites. So it has taken quite a lot of time to kind of introduce this way of thinking because it's not very common here in Norway.
Yeah, and likewise here, and this is what the industry is grappling with, this monumental change to the way that we think about the entire program. Well, that's all we have time for. Thank you so much for being here. I can tell that the audience got a lot out of that because of the activities in the chat. Thank you for getting up so early and giving up your time to tell us all about your amazing projects. I'm sure we'll hear about you again in the future at some point in time.
Thank you. My pleasure.
Thank you. Before we go, I would just like to say the Australian Timber Design Awards for 2023 have just been completed, and let's say congratulations to ARM Architecture for the Sydney Opera House Concert Hall renewal. And that is it for the webinar series for WoodSolutions for 2023. So thank you so much. The next keep an eye out in your inbox for the links to the next webinar. We'll definitely be picking this up again in the new year. So with that said, thank you so much for being here, Jørgen. It was a great pleasure to meet you and a great pleasure to discuss those buildings with you. And we'll see everyone in 2024. So Merry Christmas and Happy New Year, and we'll see you all then.